Hey guys, just want to come and talk to you today about some important questions of biodiversity. Uh, you've been reading in the Sixth Extinction about things like the latitudinal biodiversity gradient, species area relationship, and so forth. There's some stuff you've learned about back in biology that's also quite critical here. So there's some stuff that I want to sort of bring together because as we move into questions of climate change next, um, it's going to be really important for us to think and conceptualize about what our local environment here was like, has been in the past, the deep past, and then what it might be like in the future if the trajectory of climate change continues. So let's explore this a bit. The first topic that you've run into is a discussion of the latitudinal biodiversity gradient. Now, I'm going to give you the PowerPoint of this as well, but there's a great video discussion of this that I'd encourage you to check out. It does a great job discussing it. But basically, what this means is today, in today's planet, we have a gradient from the tropics to the poles where species diversity, decreases from the tropics to the poles. So basically, from 0 degrees, when you increase in latitude either direction, you lose species diversity. This is a general trend, and of course, there's some wiggle room and some variation as you go along, depending on land mass and so forth. But generally, this is the situation. The paradox here is, and I've got this. The paradox is actually down here. Is that tropical land and tropical seawater are very nutrient poor. So generally, you wouldn't expect there to be a lot of diversity in the tropics. The biodiversity itself creates the biomass, makes it possible for there to be all that biodiversity because of the amount of recycling going on, and that's part of it. The other part of it is, of course, these other things. The tropical forests are generally older. Tropical forests also have seasonal stability, so you don't have the fluctuations annually where you have to really adaptable between summer and winter. I mean, think about it. If you never had to have winter clothing and you only ever had shorts and t-shirts, I mean, your job getting up in the morning would be a whole lot easier, right? Um, there's lots of warmth, lots of water. There's tons of available niches. So where specialization becomes really, really, really advantageous and possible. And so, of course, adaptability is not nearly as necessary. Adaptability, the point being that specialization, it's easy for evolution to create specialization. It's more difficult for evolution to create adaptability. And then, of course, it's also possible that the rate of evolution is generally higher today than at the equator. Oh yeah, less variation in day-night change as you go along with the seasons. Of course, generally in the temperate latitudes, you don't have the same length of day and night, right? And so that does affect things. I mean, my chickens lay eggs better during the summer than they do in the winter, and that has more to do with daylight than it does temperature. Well, both are a factor, but daylight's the big one there. So here's a depiction of that from satellite view, but here with the false colors, of course. And you can see how biodiverse, red being high species diversity, and of course bluer, darker bluers, lower diversity. And you can see that the poleward shift, the poleward lack of biodiversity, and the equatorial biodiversity highs, but particularly in the Amazon. I mean, you hear people harping about the Amazon, the importance of the rainforest. Well, there you go. That's one of the big reasons. Now, there's a great paper, and it's linked here. Again, you'll have the PowerPoint. You'll have this version of it here from Mannion et al. And they talk about why is this the case? Why are the tropics so diverse? Are the tropics one of these three models? Are the tropics the cradle of species where extinction across latitudes is basically equal everywhere, but where the species diversity is just high in the tropics, right? So it's the cradle of new species, right? They move out of the tropics, and irrespective of extinction. Or is it because the tropics are kind of a museum of species that once were, or situations that once were, where extinction is lowest in the tropics and highest at the poles, and where origination doesn't really change depending on latitude? Or is it the situation where these are inverses of each other, where origination and extinction are complete inverses, and that in places like the equatorial regions, you have high origination rates and low extinction rates, and that leads to all that species diversity of the tropics. these are great questions, and these are three models for why this is the case. It's important to note the species diversity or the latitudinal biodiversity gradient that we see today, has existed in the past, but in the deep past, it's also not existed. There have been times, and I'm thinking about the times here that are in these open circles in particular. You note that the open circles are between 30 degrees and 60 degrees north. These are times in the Earth's past where the most diverse latitudes were in the temperate regions. And so, of course, most recently, the Paleocene Eocene thermal maximum time period, and there's really two times in the Cenozoic era where that was the case, and of course the late Cretaceous. And if we look specifically at the late Cretaceous, and what that may have looked like, you had most of the diversity is up here in these mid latitude areas, especially in the north. Part of that could be just due to the amount of land mass up there. Another time when the species diversity was much like it is today was during the late Ordovician across the extinction boundary. And of course, in that time, the tropics in Laurentia have the most species diversity, and Baltica and Avalonia have much less species diversity across the extinction boundaries. So the species diversity in these lower latitudes, or higher latitudes rather, was lower initially than it was at the tropics, which made them more able to weather the extinctions across this ice age boundary in Laurentia. Anyway, the point is that the LGB has changed over time. I should say the LBG. I have this all backwards up here. All right. So that leads to another important biodiversity pattern that we discussed in the book, or that Elizabeth Colbert discussed in the book, and that is the species-area relationship. Generally speaking, for a given environment, all right, we have this relationship that's linear, and where species richness is equal to C, which is a coefficient that's actually serves as, in reality, it serves as the y-intercept in this equation, is directly related to the area of the area we're talking about to the z power. And z, of course, is dependent upon the organisms and the environment, and as is c in many ways. So for a given environment, as a increases, generally speaking, as a increases, so does s. Okay, and of course, there's a limit to this. At some point, the areas you're talking about begin to lose any increasing species diversity because you've kind of homogenized the region, right? So you can have a continent like the U.S. You can try to do the species area relationship for, say, winged animal. You usually do it for a group of organisms, is what you do. And you look at it from a particular landscape, a group of organisms within a particular type of environment or set of environments. As you expand the area, you incorporate other environments, and you have a lot of the same environments overall. But eventually, you reach a point where there's so much area that you just aren't gonna have an increase in species diversity. So, like all natural laws, there's limitations to this. Originally, Alexander von Humboldt observed this relationship. It was E.O. Wilson and his co-author who quantified it. But again, that's what these values mean here. So we're really concerned about the z value and the c value. So what do those mean? If we look at these values, okay, if we graph the function, now it's linear. We typically represent it though as a log function, and then that's where it really gets its linear form. So s equals, and there's supposed to be an equal sign in here, ca to the z is equivalent to the log of species diversity across as a function of the log of c plus z log of the log of a, right? So we graph it like this. This is what it looks like in this form, and then of course when we put it on a log scale, we end up getting a straight line. So in log space, it's a linear function. So anyway, two different curves, same result. Bottom line is that the z value determines the slope of this line, and the c value is where this line intersects the y-axis. Okay, so I drew a little model here, a couple scenarios. My drawing is awful, but you can get an idea here. So species diversity increases along the y-axis over here. Area increases along the x-axis here. We have three scenarios, A, B, and C. A has the greatest slope, so the Z value will be the highest. C has almost no slope, so its Z value is going to be very low, actually almost a slope of 0 practically, right? And Z values don't generally have a slope of 0, but let's just say for the purposes of this that it does. We also have kind of in between value of B. We also have these running into the y with different y-intercepts, right? So they've got C has got its y-intercept way up here, so which means that species diversity starts off very high in a small area at this particular scenario, and as area increases, species diversity in this scenario doesn't increase at all. It pretty much stays the same, irrespective of area, which is why this scenario is so weird. It doesn't usually work that way in nature. In this case, scenario A, species diversity is starting off at a relatively high, moderate level, and then increases as A does, but increases more rapidly than it does at B. And so there's some variable involving the situation with A, the Z variable, that causes species diversity to increase. So there's a couple of papers you're going to look at that give you different slopes and y-intercepts you can play with. The C value is less important. I'd be considering that as far as like mostly an environmental situation. So what is our environment? Choose that as your C value. I'd be curious to see what you come up with for Z values. So what is it you want to model when it comes to Shenandoah Valley biodiversity over time? We'll get to more of what I'm getting at with that here in a moment. But okay, so that's all well and good. But what do we do with these curves, right? I mean, these are things we can go out and actually take plots of land and calculate and actually count things, and we come up with that relationship. It's really cool. David Tillman did this. Studied 2 plots of land for 20 years. One was a highly diverse ecosystem. One was a grassland, and so much less diverse, much lower species richness. And he, in the end, came up with something called the diversity stability hypothesis. That is, the species richness in an area leads to much less variation in biomass. So, in other words, you don't get, with environmental change, big weather events or even just big environmental events. Typically, places that have high species richness will have less turnover in biomass. And so what that means is less extinction and recovery. So more stability is what that gets at. So lack of species richness leads to lower stability, lower levels of stability. And this is important for questions of extinction. So if you're in a situation, for instance, in the Anthropocene here, where you're decreasing species diversity in many places around the globe, let's take the Appalachians, for instance, because we are in a biodiversity hotspot, as they say. We'll look at that more later. If you decrease species diversity in some way, maybe through habitat fragmentation, as discussed in the book, or other ways, you make the area much more susceptible to extinction. And that is a really, really important thing to keep in mind. That can happen here. This all plays into E.O. Wilson's ideas surrounding island biogeography. And I'm not going to spend a lot of time on this, but this is, again, some of the patterns here. So if we take the species area relationship and so forth, and we apply it to islands, like actually pieces of land out in the ocean, right? Islands that are closer to mainland versus being far from mainland, and of course, island size being important here, small islands, large islands. If it's a small island close to mainland, okay, one of these, the blue lines, are the rate of, or probability of colonization. You might call it origination rates. And then the green lines are extinction. And then where they meet is a balance point or an equilibrium point, okay? So this increasing species richness is down along the x-axis. For large islands that are far from the mainland, you tend to have higher species richness, but you'll have, in those areas. And smaller islands close to the mainland will have perhaps a little lower species richness, but the origination and extinction rates will be higher. And because closer to mainland, you're able to get migration of unique species to those areas, bringing in new genes and so forth. If you're far from the mainland, that doesn't happen as often, and so the blue curve is depressed here. And then, of course, on small islands, you get very few species, very few. You get a lower species richness when it's further from the mainland, because you only have a smaller gene pool, so to speak, or a smaller group of species that are endemic to that over time. And so, anyway, these are ways we can study islands. Now, we can have, of course, as Colbert talks about, islands on dry land, right? And this is a situation where we can, where we ask ourselves, if we fragment our environment, how do we affect biodiversity? The Shenandoah Valley is fragmented. If you look at it, you're going to look at a Landsat image of the Shenandoah Valley for the discussion post you did this week. You notice that there's patches of forest all over the place. Well, because of farmland and towns and other things like that, roads. Those are all forms of habitat fragmentation. But what happens when we do this, right? We end up decreasing the areas. We have little islands of ecosystems, right? Small little areas. And as the areas of the ecosystems get smaller, species richness also decreases. And part of the problem there, part of the reason for that, is that certain species aren't migrating between those islands. Now, keystone species, the panthers, they might do it, or the large mammals, for instance. Even some of the reptiles, a tortoise might make its way from one island to another. But at some point, there's a lot of species that don't make their way from one island to another, and you disrupt the trophic levels, and you end up with much less diversity, not a full collapse of the ecosystem, but you end up with potential collapse of the ecosystem. One of the solutions for this are wildlife corridors. You've probably heard of these. This is an example of one near Banff National Park in Canada, and this is another one they just built in Utah. $5 million overpass just for animals, and it's actually they're documenting how much it's helping actually to separate or to allow animals to go from one side to the other. But what about other kinds of unnatural barriers that exist and split up ecosystems? This is not meant to be political, but what about the border wall, for instance? The border wall is a great example of a boundary that keeps certain species from moving through their natural range. Or how about pipelines? Pipelines, you may not realize this, but when you put a pipeline in, you have to maintain that you can no longer allow trees to grow there. This is in Pennsylvania, and this is in Alaska. This is the Alaska pipeline, and you can see there's they keep everything pretty low there, and there's a reason why. Of course, that one's above ground because of permafrost and freeze and thaw. This one's below ground, but you can see pipeline paths around here, and you're creating islands on dry land. You're creating separation of forest. Well, why do we even care about biodiversity? Is it just because we love the cute little fuzzy animals? Well, maybe a little bit. But overall, it's because we depend on them. We aren't going to survive unless we have all the species that we depend on surviving. It's all interconnected. And of course, there's an ethical question there as well. But let's remind ourselves of the trophic pyramid. You've learned about this before and how important everything from the light energy, right? The light that comes from the sun, we can't process that. We have to rely on other organisms to process that. They're way at the bottom, right? The primary producers. And it's only 10% of their energy that makes its way up for each trophic level. And so by the time it gets to us, we're only looking at 2,000 calories per square meter per year, whereas down here, we're looking at 20,000 calories per square meter per year. And so there's a whole lot more energy being processed down here than what makes it up to us, right? And then a lot of heat, a lot of energy lost in other ways. But we are, of course, recycling some of that energy through our own dead bodies or through our waste. That comes back to decomposers, and it becomes part of this whole thing again, right? So there's some loss, but there's also a lot of recycling. Okay. Now let's talk about there's been a lot of hypotheses out there about biodiversity. There's what does it mean if you have ecosystem function on one axis and you look at biodiversity on the other? If you think about when biodiversity decreases going from the right to the left here, if you have a situation where you have lots of redundant species, which is not typically the way things work, then you can go through a lot of biodiversity loss before you really start to affect ecosystem function, right? You can have a lot of dead organisms before you really start to see an impact. There's also the rivet model, which goes back to Niles Eldredge, where it's like a plane flying in the air, losing a rivet at a time. Every loss of a rivet, or every loss of a species, leads to much less function, and eventually, the plane will come down out of the sky because the metal will rip off of the wings. There's also the linear version here, which is more like what the Tillman model, and then there's the idiosyncratic models, which are really interesting. I'm not going to get into those here, but Why do we care? Because biodiversity hotspots are things that we need to be mindful of. These are places, especially for particular organisms, that where these are locations where they typically are most diverse and where most of the gene pool or the genetic flourishing is located. So, for instance, along the eastern mid-Atlantic, you see a lot of repetition in these images, as you see. These are from the Biodiversity Mapping Project, but you can see where birds are, the greatest number of endemic birds and where they live. This upper neck of Florida is a really important place, along with the Atlantic coast and Gulf Coast. How about mammals? Again, the U.S. Southeast is a very biodiverse area. And of course, the question is, are we doing a good job preserving that? Amphibians. Amphibians in the Appalachian area, especially eastern Tennessee and western North Carolina in particular, are extremely important. We'll come back to that. Well, check this out. Check this out. Look at that. This is just salamanders. Globally, most salamanders, the most species richest of salamanders is in the Appalachian Mountains. Did you know that? What happens if they're all gone, right? Reptiles. Again, the Southeast is really important. If you notice the West doesn't have a lot of species, a lot of biodiversity when it comes to as compared to the Southeast. Much wetter here, much more consistently warm and wet. The humidity matters. And of course, the stability of the climate matters. Fish, if you're living in Mississippi and Alabama and Tennessee, you're loving it, right? But yes, endemic fish species are much more diverse along those areas. And then, of course, tree species, much more, again, the U.S. Southeast is very, very critical. So there's some areas that some scientists have identified as priority areas, including the Blue Ridge and Florida and so forth, and out here in the California around these areas where species richness is great. These are greatest. Now, of course, at our latitude, we are not nearly as diverse as the Amazon, but that's part of the problem, right? We don't have as much species diversity, and those places where we do have great species diversity, we want to work to protect those areas because it's really important that we do, because we survive because of them. So that's really important. All right, guys, I'm going to leave that there, and we're gonna in class we're gonna create a model of some species diversity in the Shenandoah Valley, and we'll take that and move into climate change from there. But feel free to ask questions.